So, good afternoon. It is time to start our seminar. So, as you know, this is the number 7 and this sequence of seminars in which we are discussing research challenges for advanced cyber physical systems. So today, the invited speaker for this session is André Rocha, and he will make a presentation about distributed cyber physical systems, especially applied to manufacturing systems. So as in previous cases, first we'll have the presentation and then we'll have some time for questions and also for discussion. So it's not questions and answers only, but all of you are then invited to also express opinions or different points of view about the subject. And for that second part, I invited Manuel Barata to be the moderator of that session. So we can now start. So I will give the floor to André.
Thank you. First of all, thank you very much for the invitation. I hope you can see my screen now.
Yes.
Okay. So, good afternoon. As Professor Camarino said, I will talk a little bit about the design and implementation of distributed cyber physical systems in the context of manufacturing. And I will start with this slide. Although this slide, I will visit this slide in the end of the presentation again, because this research topic started some years ago with the main idea of dealing with new market needs for the companies, such as the demand for high customized product, low small batches, and constant change of goals. And because of that, it was necessary to explore highly dynamic, flexible, and reconfigurable manufacturing systems that since the 70s, from the third industrial revolution, was based in industrial automation. And since the 70s, we saw that the technologies are mixing together, and currently we have an integrated architecture. So nowadays we have in the factories and in industrial environments, we have the application of this 5-layer architecture, as known as well as ISA 95. And now we need to go in the next step. As I said, currently the factories are operating with this very rigid and monolithic approach, where we have these 5 layers. So the first layer focused in PLCs and machine control. Then we have the process control with the standard supervision approach with dispatching, monitoring, diagnosis, and so on. On top of it, we have manufacturing execution systems and ERPs that deal with the operations management and the planning and logistics. And this traditional approach is quite good when we are dealing with mass production, but currently we are facing a new challenge, and the market is constantly changing. And what a change we had in the last year. So in the current times, we have not only the topics I presented previously, but a completely new reality where we need to deal with this situation. And the first approach presented was the idea of using cyber physical systems, where all the physical entities in a production environment should be connected and work together in a network. And based on that, there was some ideas that brought from that idea of using cyber physical systems. The first one was the idea of connecting everything inside the factory. And in this case, we are talking about the vertical integration. Then we had the integration in the supply chain. And in this case, we are dealing with the horizontal integration, where we link all the different factories, the different transporters and suppliers. And on top of it, after this first approach for the horizontal integration, we had also the exploration of using data also from the product and the ability for this product to share data and to contribute to this environment. And of course, the end-to-end engineering. Now, the product is developed and designed during the entire value chain and not only inside the factory or by the design departments. And all these functionalities are supported by new emergent technologies, and that there are highlighted as the acceleration of manufacturing. So these new technologies will contribute to the acceleration of manufacturing. And of course, cyber physical systems is one of these new emergent technologies that will allow this the creation of these highly complex and integrated ecosystems. And this will generate new business models. So as I said, the work started with the vertical and horizontal integration, where is the most of the focus in this presentation. And I will start with the vertical integration. Starting with the vertical integration, or before I start exploring some experiments we did about vertical integration, I think it's important to clarify a little bit about what is cyber physical systems and the concept of cyber physical production systems. So the usual definition of cyber physical system is that each physical component should have a cyber representation at the cyber level, and this cyber representation work together with the physical part in order to create an unique entity with the physical and the cyber level working together in a closed loop. And the communication among these cyber physical components, let's say, is performed mainly by the cyber level. This will reduce the complexity of integration and interoperability among different hardware and software providers, and will allow this interconnectivity we were talking about in the beginning. In order to end, of course, cyber physical production systems is the application of cyber physical systems in the context of production. In order to develop cyber physical systems that effectively solve the problems we need to solve, and to bring the added value of cyber physical systems in a production environment, it is necessary to combine these three main areas. The ICT area, because of the networks, the data, process the data, and so on. Computer science, topics such as artificial intelligence, big data, every type of algorithms, and so on. And manufacturing science and technology, such as industrial robotics, process optimization, or automation, everything that is related with the process itself. The first experiment and the first experiment I want to share with you is that this first approach we did in designing modular distributed control systems. So the idea was to develop a control system at the shop floor level where all the resources, in this case, the resources are machines or operators or, for example, a conveyor belt or a robot, is abstracted by a cyber entity, and the product is also abstracted as a cyber entity, and the control of the system is provided by the interaction among these cyber physical components or cyber physical modules. So each station and each component of this environment is abstracted by a cyber entity. For example, in this case, each conveyor belt and each station is abstracted by a cyber part. For example, this product here is traveling in this carrier is abstracted by we call the product agent. This robot here is abstracted by resource agent, and so on. And the behavior of the system as a whole comes from this interaction, and not from a standard monolithic approach. And since the behavior is the combination of the interactions among these entities, the system is capable of dealing with changes. For example, this station here that receives the result of the test we performed in these stations, put the red or the green label according to the result of the test. This station can be plugged in this point of the system, or we can change this station to another point of the system, and the system is capable to readapt and to reconfigure according to the new requirements, because every time a product requires a capability of the system, the product will ask the different entities which entity can offer this ability. So this is the example. In this case, the person just remove the station from one point of the system to another point of the system, and the system can automatically adapt this new to this new layout. In this case, we are also testing with a simulated environment. So in this case, this kind of a simulation module that we plug here, and the system can interact, because for the cyber entity, it doesn't matter if we are dealing with a simulation or a physical component, because the cyber entity is controlling the simulation or the physical entity. For the cyber entity is exactly the same, because all the interactions among the cyber entities performed at the cyber level. That's why this approach of using distributed cyber physical systems reduce a lot the effort required for the integration and the interoperability when we need to change a production line. Of course, this line was completely developed to demonstrate these concepts. This line is basically the demonstration of using small production lines to produce different products and different variants. So the idea is to have, because we will see in the next slides, in the end of the presentation, we are going to smaller production plants, and we are going to small factories where we can provide more variants of the product, and the quantity is reduced. So it is important to have kind of a network of conveyors that can be used for different purposes. As soon as I remove these modules here and connect new modules with new capabilities, I can produce different types of products using the same loop of networks, of conveyor belts, sorry. And of course, these new emergent technologies are not able to deal with, or the opposite, the traditional diagnosis approaches, monitoring, and so on, scheduling, for example, are not able to deal with these new emergent approaches. So it is necessary also to explore which kind of approaches can we use to deliver new self-diagnosis and self-healing capabilities. So one of the other experiments we did was to explore the concept of artificial immune systems algorithms to provide self-healing capabilities to the system. This is quite challenging topic, and the idea was to mimic our body's immune system to deal with problems that the system can have. And in this case, we found that three algorithms are commonly used to mimic our immune systems. We made some experiments with these three algorithms, and we evaluate the performance of these three algorithms using evaluation model. Based on the experiments we did, we selected the immune network theory, and using this algorithm, we also provided this architecture that will use this algorithm to detect problems when the hardware is running, and try to deal with these problems, trying to healing this situation. Although this architecture is focused in this self-healing capabilities, the idea is to embed these functionalities with the previous scenarios I just presented, because what we want is basically the module that is capable of control, assess if the execution is running according to what is expected, and if not, try to find mechanisms to dealing with that failure. But in this case, since we were making some experiments, and in order to reduce the complexity of the system, basically we have what we call diagnosis agents that are always checking if the execution is going well, and if the execution is not going according to what is expecting, we will call the artificial immune system algorithm to generate B cells that can be possible cures to the problem that the system is facing. And in this sense, it is necessary to develop new approaches in order to provide the same mechanisms we have with the traditional production systems, such as I said, diagnosis or monitoring. Because if we remove everything we already have and just put a new emergent approach capable of dealing with all the disturbances and so on, but we are not able to check if the system is running according to what was expected, of course we have here a gap that we need to solve. And another study we did was because we realized that although the companies present that we need to deal with new market needs, new requirements, and so on, and The companies also told us that, of course, we need to have this kind of systems running in our factories. The real situation is that most of these systems are not applied in real industrial scenarios. So we have some experiments with good results, but we don't have a follow-up. We have solutions. We find in the literature a lot of approaches, for instance, for planning, reconfiguration, monitoring, diagnosis, quality control, etc., but or we are dealing with low TRLs, or if we have high TRLs, the problem is that we don't have a continuation in these deployments. And based on this revision, we realized that in order to increase the adoption of this approach, it is necessary to reduce the integration effort. It's necessary to design strategies and methodologies that will help in this integration. And another important issue is the lack of knowledge. So for the companies, it's quite difficult to adopt this kind of approaches due to the complexity of these systems. So what we explored was that maybe it could be useful for the companies to develop solutions that will reduce the impact in the current situation of the factories. I know it seems a little strange in this presentation, but the idea is to use the concept of minimally invasive. Usually we see this concept for surgery, and the idea was, if we use the same approach in the design of cyber-physical production systems, maybe we can improve and increase the adoption of these systems by reducing the change that are required in the factories. Of course, the first experiments I shared with you are more than okay for new factories that can be built from scratch to have the hardware required for running that functionalities and to deal with all that complexity. The problem is that most of the factories already exist, and we need to somehow provide strategies and approaches that can be applied in current factories in order to start this process of using these emergent technologies. And using this concept of minimal invasive, we presented the concept of minimal invasive distributed cyber-physical production system. The idea of using minimal invasive solutions is that we should avoid as much as possible to change the current machinery and the current software we already have in the factory, but we should try to bring new functionalities using these new technologies without requiring a lot of changes in the production line. For that, we define what is a native system. A native system is basically what we already have in the factory. It can be software or it can be machinery, and we will have the new cyber system. And the cyber system should run upon the native system without requiring big changes in this native system. And this cyber system will work as an interface and an abstraction of the native system and will interact with new software tools, new functionalities that can be developed on top of this new cyber system. The first experiment we did with this approach was the idea of abstracting the production line as we did for the first experiment, but instead of controlling the hardware, we will just reparameterize the control logic without requiring new type of PLCs or controllers, but just small adjustment in the code that we already have running inside the PLCs. So the agents will run upon the existing control logic. The agents will detect which resources are plugged in the production line. We'll know which kind of capabilities can be offered by the production line, but the agents will just reconfigure the production line according to the desires of the product. We are not controlling the hardware, we are just changing some parameters. As we have here in this figure, the idea is the agent will communicate using a standard interface with the PLC, just to change some parameters that will change the behavior of each resource. The idea is similarly to the other experiment is that we should have one agent for each resource that we have in our production line, and on top of it we will have all the same interactions in order to understand where the component is plugged, which capabilities are available, which interactions we can perform or not. But instead of controlling the hardware, we are just changing parameters in the control logic that will change the behavior of the component. With this approach, we are already introducing new capabilities to the native system without requiring big changes from the hardware point of view, and even the control logic. We just need to make some adjustments in the control logic, and with this approach we can bring some lessons learned from the other experiments and introduce some benefits without requiring a lot of changes. Another experiment we did was more related with data extraction and data pre-processing. Because as I talked previously, if we are introducing distributed environments with this concept of modules that can interact with each other and allow an easy integration among each other, each module should be also able to extract data from that module, pre-process some data, and just share the new knowledge with the higher levels without forcing a huge layer that knows all these modules and collect the data from all the modules. In this case, basically we have one agent for each machine. The machine is working normally, and the data is being collected. In this case, this experiment, we used OPC UA to extract the data, and we share this data with the upper levels, and this data at the upper levels can be used to perform some advanced data analytics and so on. In that case, in specific, we use this data to develop predictive maintenance strategies for automotive industry. So based on these experiments, we used some some ideas from axiomatic design approach, and we built a tree of functional requirements that we should follow in order to design these cyber systems. And from these functional requirements, we designed this tree of design properties that future researchers and future software developers can use to develop cyber systems that will reduce the impact at the native system, but also bring new functionalities on top of it. So I will not explain all these design properties because we don't have time for that, but the idea is develop kind of a guideline that the future researchers and the engineers can use to guide their developments if they are dealing with current production lines and they want to develop new functionalities, but without creating a lot of mess with the current production line. So we started with very invasive, let's say, concepts with cyber entities that directly control the hardware and so on. We explored the concept of minimally invasive solutions, and putting all these two ideas together, we are now exploring the idea of control the process without controlling the hardware using fog computing solutions. What we are saying is instead of putting the agents running or the software, the cyber entities running inside the devices, the edge level devices, because this require PLCs and controllers with Windows or Linux operating systems. Instead of that, we can use some industrial protocols that these devices offer to run these cyber entities at the fog level and just trigger some executions at the edge level. And the idea basically is to have this cyber representation running at the fog level. This cyber representation will start the execution using, for example, an OPC-UA value, a service, or a socket, for example. This will start the execution inside the PLC, and the PLC will control the hardware. And as soon as this execution finished, the PLC will communicate to the cyber entity that this execution is finished. What we can do with this is we can control the process without controlling the hardware itself, but we can allow the communication about these cyber entities at the fog level that we can use to generate new interactions among these components, and we can create here collaborative behaviors that will optimize the system as we saw previously. So each module in this case, in this specific experiment we use an intelligent agent. This intelligent agent will communicate through services with a PLC, and the PLC will control the hardware. The communication, as I said, between the cyber entities or the pluggable module, as we call, is performed using standard communications protocols between the agents. So this hardware and this PLC will not communicate between each other. The communication is performed between the industrial agents. As you can see here, we are using basically the same approach as the previous one. However, we are not controlling the hardware directly by the agent. We are just triggering the execution at the PLC level. And we already performed some tests here. And that's why in the previous presentation by Professor Luis Gomes, I asked about IOPT tools for Arduino, because one of the experiments we did was, it's not this one is with services, but we did one experiment with Industrial Shields PLC that basically run an Arduino based control logic. So we used sockets to communicate between the agent and the PLC. The PLC receives the instruction and execute what is required. And as soon as this execution is finished, the result is sending to this cyber entity, and all the communication among the entities is performed at this level. And with this approach, we can reduce the complexity here. We can reduce the complexity of the hardware we require at this level, but we can deliver advanced functionalities and collaborative communications and behaviors at this level. We did, as I said, an experiment with this approach, with just an educational kit, that basically we have one PLC for each conveyor belt, and one PLC for the station, and basically we can detect which PLCs are connected and not connected. As soon as we disconnect or unplug this PLC, we can unplug the network or the energy cable. The agent will detect that this PLC is no longer available, and the entire system can deal with this disturbance. As soon as we connect the network cable again, the same agent will detect that this new PLC, in this case, so a new hardware is available, and the execution will start again, because this new hardware was detected by the agent. Okay, so, and on top of these developments, one of the lessons that we also identified was that the complexity of these systems is quite difficult to predict, and also to explain, mainly to the person that can benefit from these systems. So in order to explore how can we demonstrate, or at least predict, how these systems will evolve, we explored in the last year the idea of using digital twins to replicate the cyber-physical system. What we are doing here is not a digital twin of the physical component, but a digital twin of the cyber-physical system. So we are making a digital representation not only of the physical characteristics of the system, but also of which algorithms we are using for the interactions, and which are the parameters, for example, that the agents are using to optimize the system and to deal with all the complexity. And basically what we have here is using the same system I just presented. So basically this box here is the multi-agent system that was controlling the other previous demonstration. The idea is we extract the data of this multi-agent system, not only the current physical representation of the system, but also which characteristics of the system we have from the cyber entities itself, and we store this information in a file that describe the current status of the system. And I can use a simulation module that will simulate in a high-speed way this current situation of the system in order to simulate KPIs that we will have in the future. For example, if I want to know the number of outputted products by the different type of products in 1 hour, it's quite difficult to predict this with these emergent technologies. Because with these emergent technologies, we never know exactly how the system will optimize itself because of all the interactions we have between the different cyber physical components. For instance, the average cycle time, the average throughput. The idea of this test was to demonstrate that if we build a simulation model that mimics the interactions that will occur in the cyber physical system, we can predict some values and demonstrate to the human that the system in 1 hour will have these KPIs. The protection plan is in 50%, etc., etc., etc. This was just the first approach we did. We had very interesting results, and on top of this development, it's possible to start. Here is just the demonstration of this scenario I just presented. I will just go because we are running out of time. So basically, we are using the same multi-agent system that I presented in the previous example, but we use any logic to mimic the interaction among the different agents, and we can run this. This is simulated. This is not the real system. We are simulating the system in order to predict these KPIs in the future. This as a visual representation, so we cannot run this in a higher speed, but without the visual representation, we can run this in 100 or 1,000 times the real time, so we can predict the behavior of the system. And of course, after these experiments, we immediately started exploring new possibilities. And one of the ideas that generated from that work was, if we can create a simulation model that predicts the behavior of the system and the KPIs, maybe we can use this simulation model to simulate different scenarios and to reparameterize the cyber physical system. For example, the first scenario I presented, we specified expression that basically says the cost from moving a product from one point to another point of the system. This is expression based on the length of the conveyor, based on the number of products we have in each conveyor, and so on. And if we can simulate different scenarios, maybe we can use different expressions and understand for each state of the system which expressions we should use to optimize these interactions among the cyber entities. This is just a concept. This work just started, so This is the current situation of the work. This was, as I said, we just finished that first digital twin of the cyber physical system. We collected the first data. The data was quite promising for what we were expecting, and now we can start exploring this approach to generate more scenarios on top of it. So now I will talk a little bit about horizontal integration. As I said, the horizontal integration focus more at the integration of the supply chain. In one project that CTS is involved in, this quite important partner, because we are responsible to coordinate the activities related with all the ICT infrastructure. And basically, the idea is to develop a multi-layer infrastructure where we can share data and optimize the system at different levels. The horizontal integration, of course, will focus in this layer here. The idea is to develop an integration layer, an interoperability layer, where we can share data among different software tools. For example, software tools focused in lifecycle assessment, some tools related with traceability, for example, using blockchain technology for certifications and so on, ERPs, or other functionalities, and also develop interoperable layers that can not only integrate all the software tools that we have in machines that we have inside the factory, but that can also share data with the cloud and vice versa. So this approach is being explored for different industrial scenarios. As I said, this is a running project. So we just did some experiments. For instance, the developer of a manufacturing execution system that will run not only inside the factory, but also outside the factory in different levels, and will share information at both levels, because this data will be used to dynamically allocate the production for different factories of the same group. And we did also an experiment regarding the interoperability at the different levels. This first experiment, basically we did an integration using a software that is called Apache Kafka, and we can extract data from different machines at the shop floor and share this data at the cloud level for, in this case, because as I said, this project is only one and a half years, so we have one and a half year more to integrate everything. But the idea is to extract the data from the shop floor, store this data at the cloud, and at the cloud level, we should use this data. This data in this specific case is data related with energy consumption, and this data will be used by tools focused in lifecycle assessment and blockchain technology to make certification regarding the energy consumption, and also make an optimization of the production according to the machines available, but not only, but also with the factories available. So we can allocate the production not only at the factory level using the machines, but we can also allocate the production for the different factories according to the consumption that we have inside the factory. Another experiment we did we are currently deploying this in a factory in the north, in Valença. This is an Italian company that has a factory in the north. It's from CLN Group, is Magneto. Basically, they make components for automotive industry. And in this case, the idea was to develop a platform where we can have all the information regarding the performance of the machines, the performance of the operators, the performance of the factory, everything together in the same tool. And this data will be pre-processed and stored at the cloud level in order for the entire Magneto group to optimize the production according to these KPIs and to this performance indicators. As I said, this is being deployed in the factory in Valença. The idea is to deploy in all the stations of the factory. They are quite happy with the results of this experiment, and they already asked us to make a prototype for the main factory in Italy, so in order for us to explore the multi-layer of the platform. So we will have a platform at the cloud level, but we can use for some data inside the factory, some data outside the factory, and for them to optimize the production and the supply chain according to the performance of the different factories. Okay, just to finish, I said in the beginning that I was revisiting the introduction slide. I kept the slide as it was because I think it was important to specify why we started this research, although these targets are no longer the only ones. Nowadays, the focus are more in not only in the profit, as we can see here, but we have also the focus in the environmental and the social aspects of the production lines. Now we need to deliver more sustainable and more basically more sustainable production environments. And one of the possibilities is of course the implementation of circular economy. And this will also bring new research challenges and opportunities for this topic, for sure. And it's interesting because as soon as we see the last experiments we just developed, we have a lot of experiments related with energy consumption and so on, and the interaction with the humans and so on. And of course, just to make a summary, this is really the last slide. Just to make a summary, so basically the research we've been developing or explore focus, I would say, mainly at the intelligent system and system of systems. Also at some points at the smart device, but I would say the main focus is in system of systems and the intelligent system. Of course, the interoperability among this and of course, and also the collaboration of these different layers. And in some points also the integration with the interaction with the human. So thank you for your attention. I'm sorry for the 10 minutes delay.
Okay, thank you very much, André. So we'll have now a period for discussion. First of all, I would appreciate if all attendants could now turn your cameras on so that we could see your faces when discussing issues. And then I would also pass the floor to Manuel Barata to conduct this part.
Thank you very much, Luis. First of all, I would like to thank you the invitation to be here, playing a big role in this in this work of today. And I also would like to congratulate André Rocha for his nice presentation. And I will confess you that for a big leg far away from this, a big leg of time far away from these subjects, I'm in fact very surprised for the ideas, the new ideas that you show to me today. I will say that in the last 10, 15 years, I've been engaged in my institute academic management. Since I have been, previously I have been working in this subject in the 30 years ago or less in my PhD work that was related with intelligent machines for manufacturing. And by the time it was a paradigm, computer integrating manufacturing, flexible manufacturing cells. So this is a kind of prehistory of what you are saying today. This was just to situate you. Of course, by that time, my dream, and that was I used it as my research subject, was to define and to identify how can we build an intelligent machine for manufacturing. Those devices, cyber physical devices that you in fact mentioned in your presentation, and that also by that time they try to embody the self-learning capabilities. Of course, things have evolved, mainly computer science and also the computer technology. And today we have a completely different scenario. But mainly the big picture is still there. How to control this, how to make this work well, and how to turn it more efficient. So I did this intervention just to situate you about any silly question I may ask, or or probably lack of knowledge on some other aspects. But that's why these sessions are for homogenizing the knowledge and share what one knows with the others. So in this, I again thank you for your nice presentation and nice overview of the status of the art. In this case, how the flexible manufacturing systems from those times evolved up to now. I don't know, I don't have here the map. I don't know if someone is wanting to talk or to ask a question. Let me see. Are there any hands raised? No. So anyone want to ask a question or to make a comment?
Yes.
Yes,
just
please.
want to make a few comments. First of all, congratulations, André. I really enjoy your presentation. And for 1.5 years, it's a lot of work and a lot of learning for my perception. So from what I understood, first you started with the previous vertical approach that people had, and you will come into a solution for a horizontal approach with an architecture that separates the several layers, like you said, from the edge for the cyber physical, and also you bring a lot of topics. I have some appointments here. So by distributing, so by considering each machinery, each edge as an agent and having a phantom agent or agent above that controls it in another layer, you have the problem of to solve of integration of all the agents, and that integration can be done in several ways and provide several solutions according, as you said at the end, the complexity for the KPIs and the parameters that you want to optimize. But you also start talking about artificial immune systems. So first you start like we are using artificial immune systems algorithms for doing a kind of monitoring of failure or a multi-objective goal, for example. We can use for both, yes?
Yes.
So you use for failure detection and correction, and you can use also for the optimization, which is artificial immune systems. I studied a long time ago, like 20 years ago, to find multi minima instead of like algorithm genetics that find a local minima. Okay.
Yeah, we can use for both for both scenarios. In that first scenario I presented, the focus was for diagnosis and recovering, but we can use also for optimization purposes. Yeah.
Okay. Then about the intervention. So if you want to do some setting of parameters, either for fault detection and or for changing the configuration, you talked about the minimization intervention. What type of algorithms do you use there? Because it is also optimization problem. Yes.
Yeah. For example, the first scenario I presented, the optimization of the system is most of the optimizations we have here are generated by the interaction among the entities. For example, in the first scenario I presented, basically each node that we have in the conveyor network and each conveyor is each node of the network is a node of a graph, and each conveyor is a link. Okay. And basically what we do is every time a product needs to travel from one point to another, all the conveyors will share the current situation of that link, and the node will see which is the cost to travel from that point to the station that the product wants to go in that specific time. And based on the result of this calculation, this node will say to the product, you need to go through this conveyor, and the product will follow this path. After the execution of this operation, the product will see which is the next operation that needs to be done, and will ask all the agents, how can I go from this point to another point? All the conveyors will say, my cost is this because I have a lot of products, or my cost is 0 because I have no products, or I have a huge length. It depends on the expression you have for each link. And so every time the product needs to make a movement from one station to another, the system will calculate the best path from one point to another, because the system is always sharing the information of the current situation.
I have a comment on that. I think it's brilliant. It's very, very nice. You represent all the process in a graph, and then you calculate the shortest path. So according, but that graph change with time. Yes, the weight of the edges.
Yeah.
Okay. I have a suggestion for you. Just if you are interested, there is a recent paper that is the distant backbones of complex networks. That calculates a metric, which is a backbone, which could be metric or ultrametric, that actually gives you the minimization, the network that is minimizes and preserves the shortest path. And basically, this is just a suggestion. If you read the paper, you can look how the network changed dynamically, so the topology, and for example, do an intersection or a union and calculate the backbone of that as a prediction of the future, what would be the minimization. But this is just a suggestion. So the other thing,
that's it. That's a good suggestion, and I will definitely.
Okay.
As I said, in that specific case, we didn't make any kind of prediction.
Okay.
Basically, the idea was to create a system as more dynamic as possible.
Okay.
We can move one station to the other side and just turn off one station, turn on again, and so on, just to have a lot of, but in some cases, it doesn't make sense to have so dynamic approach, and we can have some prediction capability.
Okay.
Yes.
So this is what I was trying to say is just you put a multi-layer network. So you have several layers for each state that you assess through time. And then you can combine all of them and well, it may help using the metric backbone for each layer, because the metric backbone, some of the links that you will have on your connections will be good for robustness, but do not play on the shortest path. But it's good for robustness, for example, for any failure. If one of the backbones edges fails, it finds another one. Okay. But this is just a comment. Then you looked into how to control the parameters to change the behavior. Okay. Then data extraction, which was very nice. So without data, we cannot do nothing. So you find a way to extract data from the edge. And that gave me into the idea when then you present this paradigm of fog computing, of federated learning. So each edge is giving to the fog and to the cloud, and probably you can use some recent, I don't know if you thought about that, some kind of federated learning. But then, okay, yes.
To be sure, no, I didn't explore it. As I said, in the last work we did, we were more focused in how to design this system in such a way that we can control the process using cyber entities without the edge, let's say. Yeah, in the edge we have the traditional PLCs or PLCs with services or so on. And how can we split this cyber entity in an entity that run in the fog and one entity that run at the edge, and not so much in the algorithm itself?
Okay, so this reminds me, I thought it was brilliant what you said, separating that, because you can do everything at the fog level. And do all the communication, and then the edge just executes and provides data, receives data and provides data. So that just reminds me some kind of federative learning. So that's why I was it's just a comment. And then you talked about the complexity that I saw at the very beginning. Once you distribute the things, you have a dynamics that is complex, because there are some emergent properties that you cannot explain from the local properties. And then you said, well, we cannot explain this to the others and things. And then you related that with the KPIs and creating scenarios for simulation. So I thought it's great. And the only thing that I would say is probably, I don't know if you thought about reinforcement learning algorithms, for example, for doing learning on this complex, because this is an agent, they are interacting, and they can optimize these KPIs as a reward or a minimization of costs, inverse reinforcement learning or reinforcement learning. This is just a comment as well. Just
okay, yeah. As I said, in the last work, the main focus was in the design and the integration challenges, because of all the industrial protocols we have and so on. We explore much more in the design phase and not so much in the algorithm itself.
No, it's amazing. You told that you did all of this in 1 year and a half. Well,
excuse me, Tiago.
Yes.
You are speaking for 15 minutes, and
yes, I just finished.
Okay.
I just finished.
Okay.
And actually, I have another meeting now. I apologize. I just finished, and I'm sorry. So I just went from the beginning to the end. Okay,
Tiago, thank you very much.
Thank you very much, and I have to go and because I have a
Thank you.
meeting.
Thank you for your contribution. Thank you.
Okay, thank you.
So we have here Ms. Terren Babu Pulikotil.
Yes.
Rose the hand, please go ahead.
Yeah.
Sorry if I spell wrongly your name.
No, no, it's correct. So first of all, a really nice presentation, and you summed up really well the distributed cyber physical systems. I have two doubts. One is in the self-healing distributed cyber physical systems. So when you talk about self-healing, you naturally have to adapt to a failure which has happened, right? So how do you use self-healing distributed cyber physical systems if the failure is mechanical? So if there is a mechanical breakdown or mechanical failure, could we implement this type of algorithm there?
Yeah, that's a good question, and that's why when I was presenting that topic, I said that it's always a difficult topic to explore, because basically you have the algorithm that will present candidates to solve the problem, and the problem can be a combination of steps to solve that problem, or a different reparameterization and so on. But that specific aspect needs to be specified for each machine and each process. You can demonstrate that with that kind of algorithm, you can generate different candidates and so on. But for each machine, you need to model how a solution is a possible candidate to solve the problem or not.
Okay, so it depends on the modeling of the each system. Okay.
Yeah.
Okay. And other thing I heard was in minimal invasive concept, you mentioned that you can either change the parameters of the PLCs instead of changing the hardware. That's one approach. Other is data extraction and data processing. I was asking, I wanted to ask if is there a way that we could first extract the data, process it, and also like a feedback, try to change the parameters of the PLC. In this way, you could give develop an information and then use this information to make changes in the system. Is that a solution? It can be.
Yeah, can be. As I said, it always depends in the system you are working with. All this approach can be combined if you want to have that functionalities. So you can build an agent that has the capacity to extract the data, pre-process that data, and if this agent somehow sees that can improve the system, changing a parameter, the agent can write the PLC this new parameter. As I said, it's just two different experiments, but we can have both approach in the same experiment. That basically it was just because in one case the idea was to demonstrate that we can reconfigure the line using this approach. On the other one, the idea was that the people just want to have agents that as soon as we turn on a new robot or a new conveyor belt, immediately a new agent is launched, and we can extract the data from that component. But you can have both functionalities in the same agent.
Okay, and is it in real time? We could develop the system in real time.
In this case, what can I say to you is we can consider real time from the agent point of view because we are subscribing an OPC UA server, but at the same time we cannot consider real time because OPC UA doesn't work in real time. Okay, so it's real time for the agent. So as soon as the value is available, the agent receives an event and share this data with the other agents and make the pre-processing of the data. But OPC UA is not a real-time protocol, so is a characteristic of the protocol and not of the implementation of the agent itself.
Thank you. Thanks for that.
Thank you.
Thank you. Any other would like to raise a question or to make a statement? Well, meanwhile, you get some new ideas. I would like to ask you about a detail in your presentation. You mentioned a new concept, at least for me, the self-healing capability of the cyber physical system. Can you describe in more detail what are your understanding of that capabilities? And I'm asking this because in abstract it is a very challenging objective, but of course it can be simplified. And I would like to clarify your thoughts in this.
Yeah, as I said during the presentation, and I talked a little bit now with Terrin, when we are dealing with self-healing capabilities, with these new distributed approaches, we cannot have the traditional supervision and error recovery approach that we have in current systems.
Yeah.
We have in the current approaches, we have a central point that analyzes all the data and will understand if we have a problem with the entire system. In this case, since we are dealing with the combination of different modules, we need to somehow explore how can each module detect the problems that they have and try to solve locally this problem. Otherwise, it's crazy to try to solve of a system that can have for example 1 million possible combination of modules.
Yeah.
So
you mean the locally the system has some extra models that can be exchanged or swapped according to that malfunction ones that you found and continue running again.
Exactly.
Some kind of automatic or self-reconfiguration locally. Okay.
It's kind of a self-reconfiguration to solve a local issue, let's say.
Mm-hmm. Mm-hmm. Okay. Yeah. Any more questions?
I think
I have one question.
Yeah, please go ahead.
It's more on the concepts and terminology. So, André, when you made the presentation of, let's say, the initial works, you were using a lot terms like cyber entity or module and agents and so on. And in the end, finally, you used the term digital twin. But at least from the way you presented it, you separate the two things. And the feeling that I got is that you are understanding digital twin mostly from the simulation perspective. So the question is, doesn't it or couldn't the digital twin concept include all the other terminology that you used in the past for modules, agents, cyber entities, and so on?
Yeah, that's a really good question, and we always having this discussion because it's quite confusing. At least the way I see it is a cyber representation of a module can have a lot of information describing the current situation of the module, but at the same time we can have just the information required to control that module, for example. And when I see a digital twin, I see more information and the information that try to make a mimic as much as possible I would say that a cyber representation can be more limited from the information that are available, but has the capability, for example, to control, reconfigure, and so on. But regarding the digital twin, we should have much more information to describe all the characteristics of the module, all the, for example, the physical behavior of the model, etc., etc.
Yeah, because for me, a digital twin would include all aspects that you have inside your cyber entity.
Probably.
So we can say that the digital twin can have different facets or different dimensions. Okay,
Exactly.
of course, one dimension is the simulation and prediction and so on, but other dimension is the control. So you can say that your cyber entity that was very much focused on the control is the digital twin of the physical system.
Yes, yes, it's true. It's true. I agree with that. With it. As I said, the digital twin is more rich from the description and data point of view. So we can say that the cyber entity is can be part of a digital twin, let's say. Yeah, it's interesting because I was remembering. I think was in the first presentation of Ricardo, we had also the same, almost the same discussion, the difference between CPS and digital twins and so on. Yeah.
Okay.
Okay. Any other question or talk, intervention from the other colleagues?
There is a hand from Luis Estrada.
Oh yeah, I was not his. Yeah, Luis Estrada. Thank you, Luis.
Yes, thanks a lot, André, for the presentation. Was actually very, very interesting to see all these concepts. I actually have a very particular question. I think it was in the slide that you were talking about the digital twin and trying to predict the behavior, because you were talking about that because of the complexity of the emerging technologies, is it in fact kind of hard to predict what is the future behavior that we may have in? So I want to know exactly how you can predict this kind of complex behavior, because for me it sounds a little bit contradictory, right? Like you try to predict something that cannot be predicted, or at least that's what I understood. So how do you do that, and maybe which algorithms you use?
Basically, what we tried to do was we know the algorithm that we use for the interactions among the different agents, right? So what we did was to mimic the same algorithm that we have at the agents that control the system in the simulation environment. In order for the simulation environment as exactly the same interactions we will have in the agent level. The only difference is we will have the same interactions, we will have the same pattern, we will have the same algorithm, but we will run the system in a different speed.
Okay, so basically you somehow know what is going to happen, right? Because you are modeling the behavior of the agents, and you are putting the same modeling in the digital part.
Exactly.
Is it right?
Exactly.
Okay, I understand.
Okay, thank you.
Thank you.
Anyone more? Well, meanwhile, I have another aspect that I would like to ask you, and is related with the security of all these systems. Of course, security is the last thing we think on when we are doing research. But in this case, you are using something that address it, or should at least take it in consideration. When we go to cloud, it is important to clarify what kind of clouds you use. Mainly, you have a project, those avant-garde project that you are doing in the north of Portugal. They are using a cloud infrastructure, and that cloud is a private one or is a public infrastructure. And how do the industry deal with that problem? Do they feel comfortable to using all their data and their systems in a public cloud? What is your findings on this aspect?
Based on my experience, all the interactions we had with companies, most of them are not comfortable in using cloud. It's quite difficult to say that probably the data inside the factory, sometimes it's a bigger issue that use a cloud that has a lot of mechanisms about security, because the only way you have for the data not be for you to not have security issues is to have a local network with all computers that are not connected with the internet, right?
Mm-hmm. Yeah.
It's the only way. But for the companies, they don't like talk about cloud in most of the companies is already a nightmare. When you that word, most of the companies, the only companies that are a little bit more open to that are companies that already have internal clouds.
Oh yeah.
The big companies that have of factories around the world, and they have their own cloud to share data and share information. They are open to it, but in this case, you will instantiate the software in the internal cloud and not using an open cloud, let's say. The only companies that start exploring this possibility is very small companies that basically you say, you can have these functionalities, you will improve your productivity, and you have two possibilities. Or you buy a lot of computers, or you can put in the cloud. And okay, I have no chance here, let's put it in the cloud. So, or very big companies that already have their own clouds and you
That's okay.
inside their clouds, or very small companies that probably have no capacity to
invest on this. Yeah.
of hardware, so they choose to put in Amazon or Azure or something like that.
Yeah. Okay. And I ask again if someone would like. Let me see if we have. Is there any hand on? No hands on.
Yeah, I mean, while we are reaching the end of the.
Okay, so Luis, I switch to you.
Okay, then I'd just like to thank all of you for attending the session, and especially thank André for this very interesting contribution, and also thank you, Manuel, for handling this part of the discussion. And now I would like also to remind all of you that our next seminar will be on the 23rd of June, so in 2 weeks from now. And the topic will be about spectral analysis and cyber physical systems. And it will be presented by Manuel Ortigueira. So all of you are, of course, very welcome to the next seminar. So have a nice holiday and great weekend.
Thank you, Luis.
Thank you.
Thank you. You too.
Thank you very much.
Thank you. Bye-bye.
Goodbye.
Thank you. Bye-bye.
Bye-bye.